Hey guys, this looks like a fun one. This is an infinite product. We're going to multiply something an infinite number of times and see what we get. If you know what to do and you want to try it on your own, pause it right now because I'm going to solve it in 3, 2, 1. This is called pi notation. The way this works is this 2 gets plugged into each of these ends, giving us 2 cubed minus 1 over 2 cubed plus 1. And this is just going to be our first term, the n equals 2 term. And then we're going to do the same thing for 3. So we end up with 3 cubed minus 1 over 3 cubed plus 1. And that's for the n equals 3 term. And then you do the same thing for n equals 4, n equals 5, n equals 6, n equals 7. And you're going to multiply all these to infinity. You're never going to stop multiplying. So how is this going to work? Well, let's do this one first. 2 cubed is 8 minus 1 gives us 7, and then 8 plus 1 is 9. So we have 7 ninths. And then 3 cubed is 27, so 27 minus 1 is 26, 27 plus 1 is 28. And we can keep going on like this, and each of these, the number on top is 2 less than the number on bottom. Since these are all being multiplied, we can cancel stuff out. Let's see if we can identify some of the factors and see if the factors cancel out. So 7 is 7 to the 1, 26 would be 13 to the 1 times 2 to the 1. 63 is 9 times 7, which is 3 squared 7 to the 1. 124 is 4 times 31, so this would be 2 squared 31 to the 1, and so on for the rest of these. We can break all of these out into their prime factors. I do notice some of these in common, but I'm not sure if I can catch what the pattern is. Let's try one other thing to see if we can find the pattern. Since this is a difference of 2 cubes and this is a sum of 2 cubes, let's use these notes for sum or difference of 2 cubes. We can factor this top and this bottom, and maybe we can get some insights from that. The n cubed minus 1 is going to be this difference. A would be equal to n, and b would be equal to 1. So this ends up being n minus 1, and then n squared plus 1n plus 1 squared. And then on bottom, the n cubed plus 1 would equal this a cubed plus b cubed. So a is equal to n, and b is equal to 1. So this would be n plus 1, n squared minus 1n plus 1 squared. Let's see if this can help us at all. So same thing, we're going to have n equals 2, n equals 3, n equals 4, 5, 6, 7, and this is going to go on forever. So after we plug 2 in, 2 minus 1 is equal to 1, and 2 plus 1 is equal to 3. And then I'm not going to go through all the work, but after we plug in 2 for these, we get 7 and 3. And same thing for all of these. You can plug in n equals 3, n equals 4, 5, 6, and 7, and you get all these values right here. So now I can see the pattern a little bit easier. This upper right number and this lower right number are going to cancel each other out. 13 and 13, 21 and 21, 31, 31, 43, 43. And then the 57 is going to cancel with whatever's going here. So all of these are gone. Let's look at it now. So now I've spotted another pattern. This lower left and this upper left, 2 away from each other, are going to cancel each other out. So this 4 and this 4, 2 away will cancel. The 5 and the 5, 2 away will cancel. And the 6 and the 6, 2 away will cancel. This 7 is going to cancel with whatever's here. And this 8 is going to cancel with whatever's here. So after we multiply forever and all these cancel out, all we're left with is a 1, 2, and a 3. So that means that this infinite product is equal to 2/3. This is the answer to our question. Let's put a box around it. How exciting. If you want to try more pi notation problems, I have this page on andymath.com. Let me know what you think, and let me know if you find any mistakes or room for improvement. How exciting.